I'm not as think as I smart I am. I'm not as think as I smart I am. I'm not as think as I thought I might be, for that's clear anybody to see. I'm not as think as I smart I am.
Welcome to Brains Matter. Today I've got Professor Duncan Forbes with me from the Swinburne University of Technology. He's the Associate Director for Swinburne Centre for Astrophysics and Supercomputing, and his main interests include the evolution of galaxies, the study of globular clusters, and the investigation of isolated elliptical galaxies. Professor Forbes, along with a couple of colleagues, just recently made an announcement of the discovery of a dwarf satellite galaxy which is being disrupted by dark matter. This discovery by Professor Forbes and company provides the best evidence so far of dwarf galaxies being swallowed up by much larger ones. I joined Professor Forbes today in his office in Hawthorne. Welcome.
Thank you.
So, Professor Forbes, what are the different types of galaxies that we know about, just to start off in a general sense?
Okay, well I guess we have, say, two basic types of galaxies. We have a spiral galaxy, which is like the Milky Way that we live in, so that will have a central bulge of stars and also a flattened disk of stars, in which you might have spiral arm structures within that disk, and that would all be surrounded by a halo. And in that halo you have a few stars, but you'd also have these objects called globular clusters, these ancient star clusters. So that would be spiral galaxies. Then you have elliptical galaxies, which look actually a lot like just a very large version of globular clusters. So sometimes they're spherical, and other times they look more like footballs. But again, it's made up of stars, so they don't have any disk at all.
So what prevents them, because presumably a lot of these stars in these galaxies are spinning, so what prevents the elliptical ones from flattening out?
Right, well, that's a good question. So the shape of the elliptical galaxies, we think there are, again, you could divide that into two types. Basically the very massive elliptical galaxies and the low mass galaxies. So for the low mass elliptical galaxies, their shape, their football shape, is maintained by the rotation of the stars, so that gives you a little bit of flattening. But for the big galaxies, their stars don't rotate at all, and there it's basically the random motions of the stars that maintains the shape of the big galaxies.
So with the motion of the stars, if we take our own galaxy as an example of that, does the sun motion within the galaxy change? So for example, are we sitting out in a particular point in one of the spiral arms, or do we go in and out and up and down in comparison to the rest of the galaxy?
A little bit. So yes, we're in one of the spiral arms, and so we orbit around the centre of the Milky Way. We believe it takes us about 200 million years for the Sun to do an orbit around the centre of the galaxy. As well as orbiting around in the disk, the Sun also sort of oscillates up and down within the disk, and so it does that on a certain time scale as well as it's going around.
With the formation of galaxies, everyone's probably done some reading to understand how old the universe is, a little bit of understanding around how the solar system was formed, for example, which is a cut-down version of how galaxies form. But at some point, is there a limit to how many galaxies will form, how many stars and so forth will form, because there's a limit of the amount of matter in the galaxy? Is there going to be a point where they're all going to stop forming new stars and just become brown dwarfs, for example?
Right, okay, well, I guess there's several
That's a long
parts to your question. Yeah, I mean, so in a basic sense, stars form from gas, okay, and most gas in the universe is in the form of neutral hydrogen, and there's a lot of neutral hydrogen in the universe. There's a lot of it today. There was even more of it in the past. So what's happened is, as the universe has evolved, we've had a steady progression of gas basically condensing and forming stars, and then that material is locked up in a star. I mean, that star might explode if it was a high mass star, but if it's a low mass star, it'll survive for a very long time. So that gas is sort of locked up in that sense. So as I say, now we have less gas available, but if the conditions are right, that gas can form new stars, so we can have new stars forming today. And you can see that, for example, by looking at the Orion nebulae. There are stars forming in there as we speak today, and solar systems forming around some of those stars. So planets are forming also out of ultimately, that gas is available.
What's the ultimate fate of galaxies, do you think? I know that at some point the Milky Way and Andromeda are going to have a very violent meeting.
Yes, it's quite likely that our sister galaxy Andromeda is coming towards us. What we don't know exactly is it's transverse motion, so it's also moving sideways, but it's certainly coming towards us. So it seems likely that it's going to collide with the Milky Way sometime in the future. That future might be about 5 billion years from now. When it does that, we have pretty good computer models to simulate what that's going to look like. And so when they come together after a few 100 million years, maybe around 1 billion years, we'll actually form a new galaxy. We'll go from having two spirals to forming an elliptical galaxy. Some people ask, well, what's going to happen to the Sun? Is it going to crash into another star of Andromeda? But it turns out that the distance between stars is so great relative to their size that stars, although they'll feel the gravity of all the other stars, they don't actually collide. So our Sun should survive that process. It turns out, of course, that on the order of 5 billion years, the Sun is due to burn out. So it could be quite an interesting time, whether the Sun will actually be around at the time that we crash into the Andromeda Galaxy or not.
And for the people who want to understand the scale, I remember reading somewhere that we're talking about the Sun being the size of a pea and the next closest star being 8 kilometres away, as an example.
Yeah, sounds about right. Yep. So that's what's happening locally with our two galaxies. On the grander scale, the universe is expanding, so in general most galaxies are moving apart from each other, and it seems that expansion rate of the universe might be accelerating with time. So they're getting further and further apart. So ultimately, the distances between galaxies are getting greater.
Okay, I'll go back to the expansion topic in a little while, but you mentioned galaxies and globular clusters before. Can you explain to the listeners what globular clusters are? Because I know that when I was younger, I thought globular clusters were actually a type of galaxy. That's not the case.
No, that's right. They're star clusters. They contain about 1 million stars, and they're very dense spherical ball, very robust objects, and they are some of the oldest objects in the universe. So if the universe is 13.7 billion years old, the globular clusters are about 13 billion years old. And our galaxy has about 150 globular clusters that surround it, a bit like moths around a light bulb. And basically all big galaxies have these populations of globular clusters in their halo. So some galaxies have 10,000 globular clusters.
So why don't these globular clusters dissipate and move outwards like the rest of the stars? Is there something that, is it just by chance that there was a lot of matter close together and that caused the globular clusters? Well,
they're within the halo of dark matter that surrounds galaxies. They're also on sort of random motions generally within the halo. So it is true some of these globular clusters do get destroyed over time. I mean, they'll get disrupted if, for example, if their motion sent them towards the centre of the galaxy, chances are they wouldn't come out the other side. So the population that we see today is quite possibly just a small fraction of what they had originally.
And the research that you were doing, the announcement from some of the research you did recently was about one of the satellite galaxies which is being disrupted by dark matter, and this has been a fairly well-discussed point within the scientific community for a while. Dark matter, does it exist, doesn't exist, dark energy and all that sort of thing. Could you give us your view of all of that?
Yeah, I guess...
And how it relates back to what you discovered.
Sure. I mean, I guess these ideas are still quite controversial, dark matter and dark energy. But particularly, I'd say dark matter has been around with us for 40, 50 years or so. And it still seems to be the best explanation that we have. That's not to say that it's still going to be with us in another 50 years. We still don't know what the nature of dark matter is. We just think it's there because we infer it from the motions of stars and galaxies. So in terms of disrupting this dwarf satellite galaxy, what we needed to do for our simulations to look like the images that we obtained with the Hubble Space Telescope was to have in our simulation have a large galaxy with a dark matter halo around it, and our little small dwarf galaxy also with a little bit of dark matter. And then when we put this into the computer, then we could reproduce the dwarf galaxy as we see it today with the Hubble Space Telescope. If we didn't have dark matter in that simulation, the dwarf galaxy would look quite different and presumably would not resemble the image that we obtained.
So does the dark matter just surround the galaxy like a halo, or is it all pervasive throughout the universe?
we think it's mostly attached to galaxies, and so it does appear to be mostly in the halo of galaxies. So if we look at a collection of galaxies, most of the dark matter is localized around the galaxies themselves, but that's not to say that they can't also be within some even larger dark matter halo. They sort of a common envelope that they might share.
Perhaps it's attracted to normal matter, for example. I don't know.
The relationship between dark matter and normal matter, I mean, it's still a point of investigation, but we know some properties about dark matter that make it quite different to normal matter. So in general, we think dark matter is not normal matter that makes up people or stars or planets or whatever.
Could be going through you and me right now.
It's possible certain types of dark matter that have been suggested, like neutrinos, have a very low cross-section to interaction. So not only do neutrinos pass through us, but they pass through the whole Earth. They've got such low interaction cross-sections. Yep, so that's one possible candidate for dark matter.
So in terms of going back to the galaxy discussion, you mentioned there were spiral galaxies and elliptical, circular type galaxies. What causes the spiral shape to form? Why isn't it just a flattened disk, for example?
Oh yeah, that's a very tough question. Okay, well, in some galaxies we do see flattened disks without spiral arms. Okay, but in others we do see this spiral arm structure, and it is quite a complex issue as to how those spiral arms form in the first place, and then how they're maintained, how they don't just wind up on themselves. So we think that there's sort of a density wave that passes through the disk of the stars that maintains this spiral arm, but there are certainly still details we don't understand about
a lot of very
how they form, how they
complicated mathematics behind it.
Yeah.
So with globular clusters, how do they actually form? Is it during the process of the formation of the galaxy itself? There just happens to be these particular sections with dark matter envelopes that form globular clusters, or?
Well, although yes, we think galaxies form in dark matter halos, it's not entirely clear if globular clusters do. So when we look at globular clusters today, there's no evidence for dark matter in globular clusters.
Okay.
So if they did form in a very sort of mini dark matter halo, they've somehow escaped or lost that dark matter. So it's an area of current research to try to understand exactly how globular clusters formed, how they predict the properties that we see today, and whether they were really associated with dark matter halos originally or not.
How do the orbits of globular clusters work? Do they orbit just like a single star or a single group of stars, and they act as one? Or?
Yeah, they act as one. They're gravitationally bound, but then they'll have relatively random motions within the galaxy. So some of them will be circular and just happily wander around the galaxy, and others will have very radial or plunging orbits that could take them right to the centre of the galaxy, in which case they might get destroyed.
Are most of them found in the bulge near the centre of the galaxy, or do you find them all over?
I find them all over. Most actually in the halo, say, of our galaxy, but there are a few in the bulge as well.
Some of your papers talk about the biomodality of globular clusters. What did you mean by biomodality? Okay, so biomodality here just means two different populations, two subpopulations. And when you look at the Milky Way globular cluster system, you can divide it up based on its metallicity. So by that I mean the chemical composition of the globular clusters. We seem to have two populations. We can look at their motions. Again, two populations, the same two populations. And if we look spatially, as we sort of alluded to, there are some globular clusters near the bulge of our galaxy and some in the halo, and they correspond to these subpopulations in terms of their motions and in terms of their chemical properties as well. And many of your papers describe the observations of particular globular clusters. So do they vary much from one another, or can we look at a small sample and infer that to be generic amongst a lot or all of them? Yeah, when you look at an image of a globular cluster, in some ways, they can be quite pretty, but in some ways they're the most boring things around, because they're just these, symmetric spherical blobs, and so in that sense, they basically all look the same. But when you start measuring their properties, then they have different properties. They have different chemical compositions, different motions. They could have different ages, but most of the ones we find are all uniformly old. So once you
just look at them in detail, you start to find interesting things about.
So what got you interested in globular clusters in particular as opposed to other areas of astronomy?
I guess I like them because they are these ancient objects, so they're like astronomical fossils. So they tell us about the very ancient universe, or when the universe was very young. And the advantage is we can study them quite easily because they're nearby, they're with us today, and just around our galaxy. The other nice thing, I suppose, is they are relatively simple objects. They contain stars that all have the same chemical properties, the same age, because they were all formed in that one big gas cloud. And in that sense, that makes them relatively easy to understand, in principle, compared to galaxies, which are very complex, because they have stars of different ages, different chemical compositions, different components. They have galaxies have gas and dust. Globular clusters don't have any of those things. Galaxies have dark matter. Globular clusters don't. So it's in that sense it's a very simple stellar population to understand. But having said that, we still don't understand them.
And you make archaeologists look like new kids on the block is what you're looking at.
In terms of the ages, that's right. I mean, archaeologists might look at things that are millions, maybe even hundreds of millions of years old. But we look at things that are billions of years old.
I'm going back to your comment before about the expansion of the universe. As we all appreciate at the moment, the universe is expanding. Galaxies are moving outwards. Presumably the light from all these galaxies are moving outwards as well. But with the rate of expansion, does that mean the expansion is happening faster than light? I know there's relativistic issues at play here, but to the layman, they would think, well, the universe is expanding. Light from a galaxy which is expanding in this universe is expanding at that rate as well, but does that mean the universe isn't expanding uniformly, it's expanding at an accelerating rate? So
that's right. The expansion rate's getting faster, it seems as the universe gets older. So I mean, one of the big questions, of course, is, would the universe collapse on itself? So we knew the universe was expanding, and if the universe had enough matter, or enough density of matter, eventually that expansion might slow down, it might stop, and then it might turn around and collapse on itself and
have a big crunch.
Accelerate, have a big crunch, exactly. But once we discovered that this expansion was not just we were not just expanding, but the expansion rate was accelerating, expanding even faster, then we can essentially rule out the big crunch. We're going to have a situation, it seems, of an ever-expanding universe. So in that sense, galaxies get further apart. The light becomes dimmer from neighbouring galaxies, and ultimately we have a universe that's going to become very dark and cold.
So Einstein was wrong.
Well, in some ways, he put this constant term into his equations. At the time, of course, we didn't know anything about this expansion rate of the universe accelerating. So he thought that constant wasn't needed in his equations. But that one way of expressing this new acceleration is with Einstein's constant. So it's yet to be determined whether it really is a constant or not. So that's one of the things astronomers are working on, to see whether Einstein's constant is indeed a constant.
The discovery that we mentioned a little bit earlier, you said that you used the Hubble Space Telescope, and as we know, the Hubble is being decommissioned thanks to certain funding agreements or lack of agreements, whatever you prefer to call it, and the James Webb Telescope was supposed to be online prior to the decommissioning of the Hubble. Was this going to put a damper on your research during that time?
Well,
and not just yourself, of course.
Sure. I mean, it still remains to be seen exactly what's going to happen. I mean, a few weeks ago, I think it was January, one of the cameras on board Hubble Space Telescope failed. It was the advanced camera for surveys. I think there's no prospects of fixing that. The current plan is to go back to the telescope and install 2 new instruments, I believe next year, I think. And hopefully that will be successful, so we'll have a couple more instruments to use on the Space Telescope and various other refurbishments, but unfortunately not fixing this failed camera. And if all went well, that would keep Hubble operational until 2010 or 2012 or so, which is sort of the time frame that we could hope that the James Webb Space Telescope will be launched and operational. So the plan is to make sure that there's no gap but a lot of things can go wrong,
Yeah.
in that sort of plan.
Sure. Are you saddened by the decommissioning of Hubble?
Yeah, in some ways, because it's been a great telescope. It's been extremely productive, and it's supplied us with some fantastic images. I guess we'll get some nice images too out of the James Webb telescope. There'll be infrared images rather than optical ones.
Yeah. And for the listeners out there, it's not a visual podcast, but Professor Forbes has got many pictures of galaxies and objects around his office at the moment, and it's a pity you can't see it, but I don't have a video camera with me. In your recent discovery, it implies that dwarf galaxies can be transformed from one class of galaxy to another when interacting with a much larger one. Does that imply that galaxies of different sizes would interact in other ways? For example, so if you have two of the same size galaxies and they collide or interact, would that have a similar sort of behaviour, or would it have a totally different type of behaviour, or the other way around?
So one of the things that certainly determines the final product that you get after a merger of galaxies is the mass ratio between the two galaxies, right? So if you have a big galaxy and a small galaxy, what you'll tend to do is, swallow up, disrupt the small galaxy and have little effect on the big guy. But if you have two galaxies that are about the same size, so perhaps going back to Milky Way and Andromeda, when they collide, they both get totally transformed, and in this case would form a big elliptical galaxy.
So how does the actual interaction take place? So you mentioned before there's a large gap between them. The two galaxies merge or collide. The gravity properties change, but then what determines the behaviour of the actual interaction? The amount, you mentioned the amount of matter just then, but is there always going to be, for example, if we have a small galaxy versus a large galaxy, versus is probably not the right term, but if they interact, is it always going to be the same type of interaction, or is there multiple possibilities with how they interact?
There's certainly some key parameters that are involved, and so I've mentioned the mass ratio. I mean, another important thing would be the inclination of the orbits, how one galaxy came towards another, it came from above or on the side, for example. Also depends, so with the spiral galaxies, which direction they're rotating. So you can imagine two galaxies can rotate the same way and smash into each other, or rotate the opposite way and smash into each other. So these things have slightly different effects on the final product. But in general, two big spiral galaxies are going to form a giant elliptical galaxy, no matter how they come at each other. Certainly the details of how you disrupt a small galaxy depends a lot on its orbit and how it comes in relative to the big galaxies.
Have you seen many examples of this apart from the discovery you announced recently?
In our galaxy there are some good examples of dwarf galaxies that have been accreted billions of years ago, but it was certainly the case that actually catching a dwarf galaxy being sort of eaten up by a larger galaxy, right in that process of it, that the examples were very rare, and so what we found was probably the best example of a dwarf galaxy caught in the process of being eaten, disrupted by the larger galaxy, and then one that we could confirm with our computer simulations.
Is this going to be the fate of the Magellanic Clouds as well?
Yes, it's quite possible. So the two Magellanic Clouds are interacting with our Milky Way galaxy. Some of the gas in the Magellanic Clouds is already being pulled off, and some of the stars are as well. So it does seem inevitable sometime in the future that those two galaxies, those two satellite galaxies, are going to merge with the Milky Way.
With your current research at the moment, is there anything special that you're working on right now?
Lots of different projects. And say, for example, I'm interested in isolated elliptical galaxies. They're the ones that are not obviously surrounded by other big galaxies or have neighbours, so they're an interesting test case to see, understand how their formation and evolution.
So how does their behaviour differ from your average galaxy, for example?
Well, the main thing about them is they're in an environment that's isolated, so there's nothing around them, whereas most elliptical galaxies are in clusters of galaxies, lots of other ones, and they could have been formed by the merger of two spirals. So the question is, did two spirals that were just hanging around each other form this elliptical galaxy a long time ago, and now we just see an isolated elliptical galaxy, or did that isolated elliptical galaxy form some other way? maybe just from a big collapsing gas cloud. So,
and how common are those compared to the ones that tend to be?
Very rare.
Okay.
Yeah. So we've gone out and collected a sample of isolated elliptical galaxies. Our sample has 36 galaxies in it. It's pretty small. Whereas the vast bulk of elliptical galaxies live in groups or clusters with other galaxies.
The big clusters, do they tend to be in patterns, so they have around about the same number of galaxies in particular areas, or are they of various sizes and shapes?
Yeah, sort of groups through clusters can range from just 2 or 3 or 4 galaxies really, all the way up to hundreds of galaxies in a cluster. One of the things we have noticed is the type of galaxies you find. The richer the cluster, the more galaxies, the higher the fraction of elliptical galaxies. So if you want to find a spiral galaxy, you would go into look in a sparse environment, and if you want to find an elliptical galaxy, you would look in a very rich environment, like a cluster.
So a possible implication there is that there's a lot of collisions during that type of interaction in a cluster.
That's right. So in the early days, when a cluster was forming, you might have had a lot of spiral galaxies and they've collided together to form ellipticals.
So does that imply that almost all ellipticals were formed by collisions, or have they formed on their own right in that shape?
Well, that's one of the outstanding questions. So some people think at least a large fraction of ellipticals formed from the mergers of spiral galaxies, but it's certainly the case that maybe not all of them did that.
Maybe I can ask you that in a few years' time. You can give me the answer.
Sure.
Coming to the end of our time at the moment, but what do you think about the proclamations of politicians to fund missions to the moon and Mars and get manned missions up there? And do you think that's where our hard-earned taxpayer money should be going, or do you think there's more value in understanding the universe and getting more of a holistic view of what we are about and our place in the universe and what we can gain from that, compared to, say, conquests, for example?
Yeah, well, it's a hard question to answer in the sense, you don't know exactly what return you're going to get. Sometimes when you go on these endeavours, I mean, you could argue that the original space program to land on the moon cost quite a bit of money at the time. But there's certainly been a lot of technological spin-off and scientific outcomes from that. So was that money well spent? Someone's going to have to answer that question. So would we get a good return on going to the moon and going to Mars? I don't know. So some projects are probably better thought out than others. Most scientists, for example, think the International Space Station has been a bit of a waste of money. They haven't really achieved much there. It seems to be mostly a political goal rather than a scientific one.
Yeah, and I've heard similar types of complaints about the space shuttle. I think the analogy I heard was it was a freight truck rather than an exploration type vehicle. Yeah,
you're probably right. In the sense it's quite an expensive way to get up into space. But it's also true you could probably do things with it you couldn't do in other ways. So, for example, going up to the Hubble Space Telescope, launching it, and then fixing it all these times, it would have been very difficult without the space shuttle.
So, where do you think astronomers and cosmologists should be concentrating their efforts on in the next few years, apart from globular clusters?
Yeah, well, clearly one of the outstanding questions is dark energy. I mean, we have very little idea of what that is, and we're just still coming up with ways of testing it. So it's relatively new to us. There's also the concept of dark matter that has been with us for like 50 years. And there we still don't know what the nature of dark matter is, and by most measures, these two things make up the vast bulk of the universe. What we see, normal matter, is only a tiny fraction. And so we understand that at some level, but these other things are completely mysterious. So these are big questions, and they also have impact in many other areas of physics, not just astronomy, of course, and just our general view of the universe.
And for those listeners in Australia, and especially those in Melbourne, Professor Forbes actually runs a series of seminars called The Universe in 3D at Swinburne University. So if you want to have a look at that, check the Swinburne website. And for those people who are interested in astronomy, what's your advice to them?
Well, stay interested. I mean, there's certainly some good magazines out there, Australian ones and foreign ones. There's very active amateur astronomical societies around. So the ASB Victoria is very active.
Yep.
You can take some adult education classes. We at Swinburne also offer an online course in astronomy that people can take, either short courses over 6 weeks or much longer courses that last full semesters, but you can work your way towards, in fact, a whole master's degree online in astronomy. So those are some options for keeping up to date. But these days, of course, the internet's fantastic. If you want to find out things, they're all available.
So those people who want to drop an email or ask any further questions, please drop me a line at mail@brainsmatter.com. I can forward that on to Professor Forbes to answer, and we can answer those in a later episode. And for now, thank you for your time, Professor Forbes.
Thank you.
As I smart, I am. I'm not as think as I smart. I am. I'm not as think as I thought I might be. For that's clear anybody to see.